All right. All right, well, thank you for the introduction. As you just found out, my name is Scott Stender. I'm a partner with ISEC Partners. We're a security consultancy, and I work primarily in our application security consulting. I'm here to talk about attacking internationalized software. So why listen to this talk? Well, first of all, let me thank you for being at this talk, because the title doesn't exactly scream written by a marketer. It is something that is a very kind of corner case type of thing in terms of software development, just like security once was, but together, security and internationalization don't tend to play very well. So this talk is about being able to use or misuse internationalization against the ends of the system designer. It is something that there's a great deal of research potential. I found a number of vulnerabilities that were based on the techniques I'm talking about here today, but I acknowledge there's plenty more out there to be found and plenty more systems that have yet to be looked at all. So I think it is something that I hope other people will pick up, take a little bit more look at. And for platforms, internationalization is a cross-platform concern. Many of the demos in this talk will use Windows as an example, but don't think that it's just a Windows-only concern or just an application-specific concern, the ones I demonstrate. It really is something that hits almost every application developer. All right, so let's launch into the basics. Internationalization. So internationalization is whatever you have to do as a developer to write your application once and have it run against a number of locales. A locale would be a cultural specific set of preferences. So things like how do we represent the code page or the characters that we want to talk in, and how, what sort order do we use when we sort text, and how do we represent timestamps and currency and a number of other things. And if you properly internationalize your software, you have to write it once, and then you can run it on English, you can run it on Japanese, you can run it on German, you can do it anywhere, and it'll just work flawlessly and in a culturally appropriate way. Within all of those areas, most of this talk will focus on character manipulation, and there's a good reason for that. From a security perspective, a lot of times what we're going after is data, and that is where representing data comes into account, and so that's why character manipulation, being able to manipulate that data in ways that's unexpected, is really the core, I guess, portion of this talk, but there are other areas of internationalization I'll talk about later that sometimes can result in security failures. So with internationalization in code pages, there are plenty of code pages. You have single byte code pages. A lot of us are familiar with, a lot of us in the United States are familiar with, the one big single byte code page, ASCII, which actually, if you're to be pedantic about it, it's a 7-bit encoding scheme, and a lot of times people just happen to put it into a full byte because computers can chomp on it well. There are a number of other single byte character pages out there, all standardized by the ISO and whatnot. There's also a number of multi-byte character schemes. And these are, again, code pages. Multi-byte code pages are ones that will represent a character based on one or more bytes, depending on how the format is determined. And examples of this are a lot of the older ANSI, Japanese, Chinese, Korean things. Things that require a lot more space in their encoding space to represent characters than a single byte would allow. And then, of course, there's Unicode, which we'll talk about in a little bit. Now, once you get everything assigned to a code page, or more specifically, once you get all of your I guess, semantic data assigned to code points inside of a code page, you have to encode it. All the code pages is just a mapping of A equals this point. But encoding that is something that is completely independent. And within encodings, ASCII is an encoding of that code page. It's a pretty simple one-to-one mapping. But UTF-8 and UTF-16 and UCS2 and UTF-32 are all different encodings that represent the same code points, and they are interesting to look at the differences between them. If you look at a lot of them, they look nothing like one another, even though they represent the same data. So that's one distinction we want to keep in mind, is encodings versus code points. So Unicode, one code page to rule them all. The idea of Unicode is to have a single code page that represents all the world's data. We're talking about today's data, whether it's English, German, or Japanese, or Chinese, or everything that's in Chinese, and everything that's dead. There are portions of the Unicode code planes that are dedicated to Sanskrit. Right? And this is something that people are trying to have a single way. We'll never have to deal with any of this anymore. As long as we put everything into Unicode and encode it properly, life will be good. So that's the idea. And there are many encodings available. I mentioned a few already. UTF-32, UTF-16, UCS2, UTF-8, UTF-7 are just some of the ones you see right away. Unicode is a 21-bit encoding scheme. Now, a lot of people, when they think Unicode, they think of 16-bit characters. Well, those 16-bit characters are called the base multilingual plane. They are the very basic set of characters that most people will be able to communicate in. So things like English and European languages and Japanese, or most of Japanese and Chinese. But there are, for people who need to expand beyond the simple 65,000 characters that the base multilingual plane can encode, can go up into the upper planes. And that's where things like Sanskrit and lesser used things are. Now, all the encoding schemes that we have are going to try to encode as much as possible. And if you're talking about UTF-32, UTF-16, or UTF-8, or UTF-7, they can encode all 21 bits. UCS2 is simply using, is simply the 16-bit code point that can only encode the base multilingual plane. Now a lot of people think UTF-16 and UCS2 are the same thing. The one thing about UTF-16, and if you're using Windows, and you know the basic character type is a 16-bit character, WCAR. If you're using one of those, you're using UTF-16, and you actually can have a multi-byte character with that. And that's called the surrogate pairs. You have Unicode D800 to DBFF and DC00 to DFFF, or FFF. Those are going to be what are called lead bytes, and this is something that we're going to go over here in a moment. But you can encode the full 21-bit character set in UCS16 or UTF-16 using those lead bytes. Now, what's a lead byte? I've thrown this out a couple times and haven't explained it very well. A lead byte is a very simple way of expanding your encoding space without breaking lead byte, backwards compatibility. So when we tried to move beyond ASCII, we had a single byte 8-bit character or 7-bit character that we wanted to be able to use with broader encoding schemes. So a lot of these encoding schemes are ASCII compatible. That means if you are going to encode the lower 128 characters in ASCII, it should be byte for byte compatible more or less. But if you want to do more, then what you do is you have a lead byte that says, I'm not a character, me and the guy after me are a character, or 2 after me, or 5 after me, in the case of UTF-8. And here's how that works. This is an example from a Japanese code page, sometimes called ShiftJIS, or in Windows, it's Windows 932. And with that, you have a lead byte and trail byte. On the lead byte, you'll see on the left is just a simple 0 through FFF, or 00 through FFFF. And you'll see that some of them are white, some of them are gray, some of them are dark gray, and some of them are blank. Now, the white characters on the left are things that are a single byte character. So if I want to encode A, which is hexadecimal 41 in this code page, I just say hexadecimal 41. Now, if I want to encode Unicode 2032, which is a code point, if I want to encode that in this page here, or in this encoding, then I change it to, you'll see that it's the first byte, the lead byte is hex 81. The trail byte, if you look over there on the 8 row in the C column is there. There's our 2032 prime character. And so together, the lead and trail byte would be 818C. So if I was a parser that was wanting to understand the ShiftJIS code page, say I was converting to Unicode, I'd go through different bytes and I'd say, okay, I'm on hex 41, this is an A. I'm just going to encode it to Unicode A, 41. If I'm going through and I see lead byte 81, I say, hey, this isn't a character, this is a lead byte. I check out what's next, and then the 2 of them I use to look up and see what is the actual character, which is Unicode 2032. So what would come out there be 0041, 00, if we were doing another on the UTF-16 thing, UTF-16 code page would be 0041, 2032. So that's how lead bytes and conversion kind of work. Any code page that relies on multiple bytes, whether it's the ANSI code pages like ShiftJIS, or if it's UTF-8, rely on this notion of I'm a lead byte and the person after me affects the actual code point that's coming out. And we will see how that can be used for malicious purposes a little bit later. Any questions so far? All right, feel free to jump in anytime. So almost every platform has support for internationalization, especially Unicode. Results depend on the Unicode standard supported by the platform. For example, platforms can be defined as platform support by Linux system programming and Windows system programming. There's also the higher level platforms, .NET and Java, or even your programming language. All these things have various level of Unicode support, and how much you can encode in them and what kind of attacks are going to be very specific to what they support. Now, if you use one of the newer ones, .NET and Java, that wasn't around when it had to worry about using ASCII versus the Latin code page versus Latin 2 versus Japanese versus Chinese. They usually don't worry about it so much. They'll support Unicode and maybe another lesser encoding and call it quits. Now, that's nice because you have less variation, less attack surface, less things to go wrong. So you could say, hey, great, best practice. All I got to do is use .NET or Java or something that's been around or created rather recently, and I'm all safe on my internationalization attacks. And that's not so much the case, because even though your application may try to keep things in one understood canonical format, you are always talking to things you don't control. You're talking to your web server, you're talking to a client, you're talking to your backend web service, you're talking to your backend database. All these things are, have a internationalization boundary and therefore attack surface associated with them. So to use a couple of platform examples, and this is just 2 samples, in Windows. Windows is built with Unicode at its core. Most native API functions take UTF-16 strings. Now, for example, I dare you to try to find the exported function create file. Just create file, for those of you who are familiar with Windows programming. There isn't one, because it is per compile defined to be either create file W or create file A. If you go with and that would be wide string versus old ANSI one. And if you use one of the old ANSI ones, then it will convert to wide car before sending it down to the actual syscall. So everything eventually gets converted to Unicode in Windows, or almost everything. I guess you could, if you don't do a syscall, you can stay all in ASCII or ANSI or whatever you want. But there's always going to be a Unicode conversion attack surface in Windows. Broad generalized support through OS and applications. Because it's so integral, and because Windows has been designed from the ground up of late anyway to be Unicode compliant, there are always some free things you get for internationalization with programming in Windows. If you use a WCAR type, and if you use the core libraries, you're just going to be able to work across different locales, and it's not going to be very difficult. Now, that's why they serve as an example, as the example for today's demos, because it does have such core support, but at the same time, everything isn't the same. If you install an English build of Windows, it's not going to have support for all the code pages and locales than the Japanese build of Windows does. And so it's something you have to keep in mind when you're testing for nationalization. You can't just test on an English machine and think that you're safe. You have to test across different builds. And character set conversion in Windows has 2 core APIs, which I'll put out as examples here. These are things that are Windows specific, but the general ideas translate pretty well across any kind of conversion. Multi-byte to wide-car. Now this is what converts from the locale-specific code pages, ANSI or ISO or whatever, into Unicode. A couple things to take note. There's the code page that you specify. So what am I today? I am Windows 1252 and I want to become Unicode. Well, there are a couple things to keep in mind there. A couple of the parameters also point out are the source and destination strings. You have count of bytes, count of characters. If you mess those up, you're going to get a buffer overflow, and that's something that's been a historical problem. Going the opposite direction, going from all of Unicode down to a locale-specific string, is carried out by wide-car to multi-byte. Now, this is one interesting area to point out here is that in the DW flags parameter, you have this thing called WC no best fit chars. Now, that means that in general, if you're converting from a many to one relationship, you can have many things that are kind of like an apostrophe. You have your standard hexadecimal 27 ASCII apostrophe, but you also have in Unicode the properly curled apostrophes that you put before and after a word. And you have prime characters, and you have other marks and things that look like apostrophes. And if you want to have, after the conversion, have it still resemble an apostrophe, the conversion can cut you a break. It'll become an apostrophe, a hex 27 apostrophe when it gets down to the locale-specific string. Or you can say, don't best fit. If it doesn't fit, make it the default failure character, which is by default question mark. So a couple of things to take away from both of these is you're always going to be converting between a locale-specific string to Unicode, which is going to be almost always there's going to be one locale-specific string which matches directly to one Unicode character. I'm sorry, character to character. Going in the reverse, you're going to have a many to one, where there's going to be